What about this question? Any doubt in this? Okay, question number 1 and 2. Okay. First question also. Fine. So just give me a moment. We'll discuss. Okay. So here what is happening is, see, this ring can slide freely on this surface. Okay. On the rod rather. And you have the light string passing over the smooth pulley at a distance of 0.8 meters. So this distance is 0.8 meters. Okay. This has a mass of 30 grams. This has a mass of 50 grams. Okay. On the distance by which the mass small m moves before coming to rest for the first time. So when it comes to rest for the first time versus when it is in equilibrium. So let's understand that. Okay. So if this has gone up through a distance of y, or let's say y1, this has come down by a distance of y2. Okay. Understood, Snikita. Acha, people, what we will do is there is a problem here. Some students have not given this exam because of KVPY preparation. So they will be taking the exam next week. I mean, in this coming weekend after the KVPY is over. So I don't want to release the question. So we will do the discussion of this in the next week. Okay. We will do the discussion of this in the next week. In today's lecture, let's just go ahead with our next chapter. Okay. So I'm just postponing the discussion and doubts of this for the next week. Meanwhile, those of you who have given the paper, if you have any particular questions, you want some hints, and just send me a WhatsApp. I will help you out with all that. Okay. So just keep the doubts ready when we are discussing next week. Currently, I was not aware that some students have not given the paper. So anyway, let's come back to this now. So currently, let's come back to our next topic, which is going to be heat and thermodynamics. Okay. So today, let's begin with the next section of physics, which is heat and thermodynamics. So this is also a very interesting branch of physics. Okay. And we will begin this branch of study with the very interesting phenomena of thermal expansion. Okay. So just before we get into thermal expansion, let us just quickly talk about the different temperature scales. You have the Celsius scale, in which melting point of ice is 100 degrees C. Oh, sorry, my mistake, 0 degrees C, and boiling point of water is 100 degrees C. Okay, so this is called the centigrade or Celsius scale. Then you have the Fahrenheit. Scale, in which this is 32 degrees Fahrenheit and this is 212 degrees Fahrenheit. Okay. And then finally you have the Kelvin scale, or what we also call the absolute scale. So that is 273 Kelvin and 373 Kelvin. So you should be absolutely clear about this. Okay. So you can also understand that this interval is 100 degrees C. This change in temperature from this to this is also equal to 100 Kelvin. Okay. But in Fahrenheit, this variation of temperature is 180 degrees Fahrenheit. Okay. So from that only you can understand that if you want to convert from Fahrenheit to centigrade, okay, X degrees Fahrenheit will convert to X minus 32, okay, into 100 by 180 or 5 by 9. in degrees C. Okay, so for example, 68 degrees Fahrenheit in degrees C. So 68 degrees Fahrenheit will become 68 minus 32 into 5 by 9. That is 20 degrees C. So this you can clearly understand the logic from this. Okay. And similarly, if you have something in degrees C, then in Fahrenheit it becomes y into 180 by 100 plus 32. In degrees Fahrenheit. Okay, so this is the conversion formula. And the conversion from Celsius to Kelvin is very easy. Okay, any x degrees Celsius is equal to x plus 273 Kelvin and vice versa. Yes, we will cover all these things. So I'll just give you a quick idea of the things we will cover in heat and thermodynamics. Just write down about the temperature scales first. So for example, convert 25 degrees C to Fahrenheit scale and Kelvin scale. Yes, very good. Yeah, that delta, correct. People will just have to make a quick correction here. Thanks for pointing this out. This is Fahrenheit. Okay. This delta T in the second one is in degrees Fahrenheit. So a change in temperature of 180 Fahrenheit is equivalent to 100 degrees C. Okay, so that is the conversion factor. So basically from this, what you can see that a change in temperature of 100 degrees C is equal to 180 degrees Fahrenheit is equal to 100 Kelvin, or 1 degree C is 9 by 5 degrees Fahrenheit, and 1 Fahrenheit is 5 by 9 degrees C, okay, and 1 degree C is equal to 1 Kelvin. This is a change in temperature. Okay. A change of 1 degrees is, okay, so obviously correct. This one will become 25 degrees C is 77 degrees Fahrenheit, and that is the same thing as 297, sorry, 298 Kelvin. Okay, so this is very basic stuff. All right. Now, before we get into more about heat and thermodynamics, let's just understand what is heat. So heat is a form of energy, okay, that always tends to transfer from a region of higher temperature to lower temperature. So at the molecular level, the heat is nothing but kinetic energy. Whatever the state of matter it is nothing but the molecular kinetic energy, which is the heat. Okay. So for solids, it is the vibrational kinetic energy of molecules. The molecules can only vibrate with respect to each other because they are strongly attached by intermolecular bonds. So you can think of the intermolecular bonds like tiny springs, and the solid molecules can vibrate about those springs, and that is the kinetic energy. Whereas in liquids and gases, collectively, it is the translational plus rotational plus in certain cases vibrational kinetic energy. So particularly for polyatomic gas molecules like methane gas or nitrogen dioxide or something like that, because the size of the molecule is large, so the atoms within the molecules, polyatomic molecules have multiple atoms. So the atoms within the molecules can vibrate about each other also. So there can be vibrational kinetic energy. Plus the molecules can move about within the body or within the volume of the substance. Okay. So they can move about in a translational manner, that is when there is no rotation, or they can also be spinning about their own axis. So there can be rotation. So there can be combination of rotation and translation, just like the orbital motion of the Earth. It is a combination of rotation and translation. So like that, fluid molecules, liquids and gases collectively can be called fluids. And in fluids, the molecules can possess translational, rotational, and vibrational kinetic energy of the molecules. Okay. So ultimately, when we measure the temperature of a material at a certain position, it is a measure of the average kinetic energy of motion of the molecules. And that is why heat flows from higher temperature to lower temperature, because kinetic energy in interaction between molecules will always go from faster moving molecules to slower moving molecules, as is the case you will see in collisions. So heat is nothing but at the molecular level, it is the kinetic energy that is transferring from a region having more activity to a region having less activity in terms of average kinetic energy. So that is how we visualize the heat energy at the molecular level. So even the sensation of hotness or coldness that you experience is because of that transfer of the kinetic energy at the molecular levels. When your hand touches a hot metallic plate or something, the molecules in that are vibrating extremely fast in comparison to the molecules at the surface of your hand. So the moment it comes in contact, there is a certain transfer of energy, and that's what gives you the heat shock. And vice versa, if you touch a piece of cold ice or something like that. So in in terms of proper definition, it is the absolute temperature. That is the temperature in Kelvin scale. That is defined in such a way that the temperature is directly proportional to the average kinetic energy of the molecules. Okay. And that is why absolute zero, which is 0 Kelvin or minus 273 degrees C, is the hypothetical or the theoretical temperature, because it is not achieved in a physics lab yet. It is the theoretical temperature at which molecular activity ceases. Okay, that means the average kinetic energy of molecule should be 0. Okay, so done with this, no? So now I will just discuss all the various aspects of heat and thermodynamics that we'll be discussing. Okay, so this is a section of physics which will have roughly 12 to 15% weightage in your JEE Advanced as well as JEE Mains. So just generally talking about this heat and thermodynamics. Approximately 15% weightage. Okay, so in this there will be thermal expansion, which is what we will start with today. Okay, then calorimetry. Okay, then there will be kinetic theory of gases. Okay, first law of thermodynamics. heat engines. This part, okay. So it is like roughly this is one slab, which is the thermodynamics part. The earlier part is the heat part. And then there is heat transfer. So this along with this actually is the heat part. So totally the weightage is that about 15%. Okay. So this just to give you an idea. All the chapters are there in HCV or in the module. I sent you a copy of the module, I think, also by PDF. Okay. But for HCV, this is in the second part of HCV. This is in HC Verma volume 2. Okay, part 2. In Resnicality, it's obviously part of the first volume for Crane. Yeah, I'll tell you the number of lectures also. So let's start with thermal expansion. Okay. So all materials, whether we're talking about solids, liquids, or gases, they tend to expand when, so the dimensions, or you can say size of a body or any material tends to expand on heating and contract or compress on cooling. So this phenomena is called thermal expansion. So for solids, okay, the laws of thermal expansion are that if you're talking about linear expansion, that is the expansion slash contraction of any linear dimension, okay, or length type dimension. Example, the length of a rod, okay, or the diameter of a disc, okay, or for that matter, the diameter of a sphere, any such linear dimension. The law of linear expansion is given by this one, that fractional change in length is directly proportional to the change in temperature. Okay. Delta L is the change in length, okay, when the temperature is changed by delta T. Okay. So the principle of this is that the fractional change, that is delta L by L, is directly proportional to the change in temperature delta T. And that alpha is just the constant of proportionality, which is called the coefficient of linear expansion. So it is just a constant. It's a physical constant, which is a material property. That means it depends on the material with which the body is made. Okay. So alpha is measured in per degree C or per Kelvin. Okay. And typically for metals, for example, for metals, alpha is of the order of magnitude of 10 raised by minus 6 per degree C. The order of magnitude of alpha for metals is 10 raised by minus 6 per degree C. So this is an experimentally determined fact that the fractional change in length becomes directly proportional to the change in temperature. It's just, it's one of the things about nature that matter behaves in this way. Okay. Okay. Now, similarly, surface area that expands or compresses or contracts according to a similar principle. Okay. So, by surface expansion, we mean the expansion or compression of any area, anything having area dimension. For example, it could be the formula pi r square area of disk, or it could be the area equal to 4 pi r square as the surface area of a sphere. Okay. Or it could be the 6L square as the total surface area of a cube, any such dimension. Okay. Or it could just be, a flat surface like a lamina. Okay. This is a laminar surface because it's lying on a two-dimensional place. Whereas these two are examples of non-laminar surfaces. They're not lying on a two-dimensional plane. So it doesn't really matter. Just a second. Whether it is laminar or non-laminar, the surface expansion works in such a way that again fractional change in area is going to be directly proportional to the change in temperature, where this time the constant of proportionality is a different term called the coefficient of surface expansion. Okay. And for any material, beta is exactly twice of alpha. I'll give you the proof of why this happens also. Beta's value is equal to twice of alpha for a given material. The fractional change in surface area will be exactly equal to 2 times the fractional change in any linear dimension when the temperature changes by delta T. So just note this down for the moment. I will explain how this exactly comes, that beta is equal to 2 alpha. Okay. I'll just show you can write the whole thing. So it's basically the two boxed formula that you need to remember, that fractional change in length is equal to alpha into delta t, and fractional change in surface area or any area is beta into delta t. Yeah, expansion of surface area. A very common example I use in real life is that if you put a glass window pane in a frame, you always need to put some rubber sealant at the edges to cover for the expansion of the glass. If you put the glass directly against an aluminium frame, for example, the glass might expand more than the aluminium frame and it might crack. Okay, so that's an absolute everyday example. Okay. Or another example is the process of riveting, as you know. Riveting is a process used to fasten bolts in sheets of metal or in metallic structures, like if you have a like a metallic beam which you are bolting onto a metallic platform or something, then you do a process of riveting where you make a hole in the metallic plate, and the hole is first heated so that it expands a bit, and then a bolt is put into it, and as it cools back to normal temperature it fits exactly. So again, that's an example of surface expansion. So when we do some numerical examples next, we'll understand that process better. But yes, there are lots of examples in everyday life around us. Okay. The best example of linear expansion is the mercury thermometer. I mean, I hope your generation is still in touch with mercury thermometers, because I know you're used to using digital thermometers more. But you might have seen the mercury thermometer where you have a cylindrical kind of glass tube kind of thing, which inside it has a smaller glass tube in which there is mercury. So mercury is the only known liquid metal which has a reasonably high coefficient of linear expansion. So the length of the mercury column inside the thermometer is directly proportional to the temperature at the at the head of the thermometer, where the mercury is in a sort of a vessel and it's in contact with whatever's temperature it is measuring. Okay, the third part of this, volume expansion. So any volume V expands or contracts according to, again, this principle that the fractional change in volume is directly proportional to the change in temperature, and the coefficient of proportionality is called the coefficient of volume expansion, where gamma is equal to 3 alpha for any material. So this could be the volume of a solid sphere, it could be the volume of a cube, it could be the volume of a cone, whatever, cylinder, cone, any kind of shape. Okay, so let us look at an example. So a thin metallic rod is of length equal to, let's say, 500 centimeters or 5 meters at a temperature of 30 degrees C. Okay. Find delta L, its extension, delta L by L, the fractional change in length, okay, and third, the percentage change in its length, okay, when it is at, say, 80 degrees C, or when it is at minus 70 degrees C. Okay. Now, given that alpha for that particular metal is equal to 6 into 10 raised power minus 6 per degree C. So the original length is given at 30 degrees C, which is measured to be 500 centimeters. Okay. So now we have to find out what will the new length become, or what will be the fractional or percentage change in length when the temperature is changed from 30 degrees C either to a temperature T1 of 80 degrees C or to a temperature of T2 equal to minus 70 degrees C. So just try this out. The principle you have to apply over here is this, that fractional change in length is equal to alpha into delta T. So just use this formula. Just substitute the value of change in temperature and alpha given to you, and from that you will find the change in length. Okay, Kevin and Snikita, your answers are correct. Okay. Only you have to be careful about the algebraic sign, when it is plus and when it is minus. So in the A part, your temperature change is T1 minus T. So it is a temperature change of plus 50 degrees C. So delta L by L, which is alpha delta T, here we will substitute this as change in length upon original length, okay, which is 500 centimeters or 5 meters. This is equal to 6 into 10 raised by minus 6 into 50. Okay, so first of all, my fractional change in length is 3 into 10 raised by minus 4 with a plus sign. So my percentage change in length is plus 0.03%. Okay, for percentage change, you just multiply with 100. So delta x by x percent is delta x by x converted from a fraction into a percentage, like this. So using that over here, and delta L itself, or you can see 1.5 millimeters. Okay, so the rod will expand by 1.5 millimeters. Yeah, Kevin, that's correct. Okay. So the first part, the change in length is so much, the fractional change is so much, and the percentage change is so much. So now in the second part, you just repeat this, but delta T is T2 minus T. So it will be minus 70 minus of 30. So it's a temperature change of minus 100 degrees C. Okay. So delta L by L will become minus of 6 into 10 raised by minus 4. So delta L by L percentage will become a negative 0.06 percentage change. Okay. And the change in length will become minus of 3 millimeters when we calculate. So this will contract by 3 millimeters. This will elongate by 1.5 millimeters. Okay. So this is like a typical actual value because this is how metals behave. So if you were to have a 5 meter rod and increase the temperature to 80 degrees C or decreased it to minus 70 degrees C from something close to room temperature like 30 degrees C, you could expect something like this to happen. Right? Hope this is clear. So second part, these are your answers. Fractional change in length is this much. Percentage change in length is this much. And the actual change in length is a contraction by 3 millimeters. Okay, Aman, I'll show you the question again. This was the data given in the question. Okay, done, Aman. Now let's come to another interesting type of question. Okay. Now this is a bit more conceptual as a question. So what is happening is the length of a plastic sheet is measured by a metallic scale to be, let's say, 600.00 centimeters at, or is measured to be 600 centimeters at a temperature of 25 degrees C. Okay. Assume that the metal scale was calibrated at 25 degrees C. So the measurement is accurate. Now, both the sheet and the scale are at a temperature of, let's say, 65 degrees C. Okay. Alpha for plastic is given to us, suppose, as 2 into 10 raised power minus 6 per degree C, and alpha for the metal is, suppose, 1 into 10 raised power minus 5 per degree C. Okay. So find the true length of the plastic sheet at 65 degrees C, and find the length measured by the scale at 65 degrees C. And because of this, what is the percentage error in the measurement? So think very carefully why the answer to the first and second part should be different. What is the true length of the plastic sheet at 65 degrees C? Whereas what is the length that the given scale will measure at 65 degrees C? And therefore, the percentage error in the measurement by the metal scale, okay, due to its own expansion. So because of its own expansion, its calibration has gone wrong. Its least count, which was supposed to be 1 millimeter, is now no longer 1 millimeter. Now, one division on the metallic scale is not an accurate value of 1 millimeter. It will be more than 1 millimeter because the metallic scale has expanded. So there is a certain percentage error in the measurement that it is doing. And that is what you have to calculate over here. So hope you understood the meaning of the question. Okay, try this out now. Okay, so what is the percentage error finally that you people are getting? .04% error. Yeah. So let me verify that with, yeah, 0.04%. Okay. So what is going to happen is that, see, the actual plastic sheet, suppose it had some length and width. So this length was equal to 600 centimeters at temperature equal to 25 degrees C. So the length will become some L plus delta L at a temperature of T naught plus delta T. So that is now 65 degrees C. Oh. So this delta L by L, this is for plastic. Okay. So this is going to be for plastic. So this change in length is going to be 600 centimeters multiplied with alpha for plastic, which is given to us as 2 into 10 raised power minus 6 into the change in temperature, which is 40 degrees C, positive change of 40. So this is going to be 6 into 8 into 10 raised power minus 3 centimeters, or so 0.048 millimeters. This is the actual change in length. Okay. So the true length of the plank will become, is this calculation correct? Yes. Okay. So this is this. Okay. Now the thing is, see, what is happening is that for the metal scale, okay, so let's say one division on the metal scale is 1 millimeter at 25 degrees C. Okay. So that same division at 65 degrees C will become 1 millimeter into 1 plus alpha delta T. Okay. Now this is also an important way to use the formula. See, what we can do is, since delta L by L is equal to alpha delta T, so the change in length is original length into alpha into delta T. So the final length, which is L plus delta L, can always be written as L into 1 plus alpha into delta T. So this is an alternate form of that same formula. Okay. So you can just keep a note of this thing also, that this formula is equivalent to this formula. Okay, so I can say like this, that the new length at some temperature T2 is equal to the original length at temperature T1 into 1 plus alpha into T2 minus T1. So this is how I can say. So one division at 25 degrees C is measuring 1 millimeter. So that one division at 65 degrees C will measure 1 millimeter into alpha delta T for the metal. Okay, so one division's value on the scale at 65 degrees C will become 1 millimeter into 1 plus, now alpha for the metal I had given as 10 raised power minus 5 into the change in temperature we saw as 40. So that has expanded to 1.0004 millimeters. So one division, sorry, at 65 degrees C, it has expanded to this. Okay, so the measurement of the sheet's length, okay, by the metal scale, that will become what? The measured value, let's say X in millimeters, will become the true length divided by one division in millimeters of this. So the true length we just saw was how much? It was 600.048 centimeters, or we can say 6000.48 millimeters. Okay. So this is 6000.48 millimeters divided by 1.0004 millimeters. So this will be the reading. Okay, this will be the reading on the scale. So it will be a 0.4% error, as you can see. Now this type of calculation we can do very easily. So how to do this calculation, let's understand. Okay. So whenever we are dividing something like this, we are dividing. So I'm going to discuss about use of binomial approximation. Okay. So if I'm doing a calculation where X is equal to Y upon 1 plus delta X, okay, where delta X is very small compared to 1. This can be written as Y into 1 plus delta X to the power minus 1. So that can now be approximated as Y into 1 minus delta X, like this. Okay. So for example, I have X is equal to some number divided by 1.0004 here. So that is N divided by 1 plus this. Okay. So this becomes N into 1 plus 0.0004 to the power minus 1, which I can now approximate as this. Okay. So this becomes the value of X. So this is the method we'll use here. So the measurement in millimeters will become 6000.48 into 1 minus 0.0004. So it becomes 6000.48 minus, now this is to be 6000 into, we can approximate this as 6000 into 0.4 to the power minus 3. So it will become 2.4 approximately. So it will become approximately 5998.08. or you can say approximately, because anyway the least count is 1 millimeter. No? So your scale will end up measuring it as 5998 millimeters. Whereas the origin, so according to your scale, what is happening is it's saying that it has compressed instead of expanded. And you're understanding why that's happening now, because the scale has expanded more than the plastic. Okay, so the interesting thing is that, so what is actually happening here is that the plastic sheet actually expands in length. Okay, from let's say 6,000, suppose we have found some way of measuring it very accurately to 6,000 point, what was it, 48 millimeters. Okay, but because our metal scale expands more rapidly. Why I'm saying more rapidly? Because alpha of the metal is greater than alpha of plastic, which you can see in the value. So the reading that the metallic scale gives us is completely false. Therefore, the reading of the metal scale, in fact, that implies that the plastic sheet has compressed. It is completely false. It's not compressed, it's actually expanded to this much. Approximately it's compressed by 2 millimeters, whereas actually it has expanded by 0.48 millimeters. So you can understand there is a certain amount of error in the measurement. Okay. So next thing we'll look at the error in measurement, how to calculate it. Okay. But you will see that the error in measurement is basically the percentage error by which the division of the metal scale has changed by. So you can see na, in the above formula that the metal scale's division has expanded by a factor of 0.04%. So the error will, which it will also give us, will be 0.04%. But the type of error it will give is that it will measure the length to be reduced by 0.04% of the actual length. Whatever is the actual length, it will report that it's less than the actual length by a factor of 0.04%. Why? Because the scale itself has expanded. So this is the important point I wanted you to understand in this question. Okay. So first of all, you fully grasp this second part, understand this, that how we calculate the measurement that the scale is making. So for that, we look at the least count of the scale. The division, one division on the scale has expanded from an actual value of 1 millimeter at 25 degrees C to a false value of 1.004 millimeter at 65 degrees C. Because the calibration was done at 25. So the calibration has gone wrong by 0.04% at 65 degrees C. So if you compare this and this, now you can see that the calibration has an error of 0.04% at 65 degrees C. It was 100% accurate at 25 degrees C, but this is 1.0004. So it is expanded by a factor of 4 into 10 raised power minus 4. So that is a 0.04% expansion. So at 65 degrees C, my measuring instrument's error is 0.04%. So whatever reading it gives us will give an error of 0.04%, which I will show next by calculation also. Kevin, it should be 0.4% error. Let me check. See, what is this value coming to? 4 into 10 raised by minus 4, na beta? See, alpha delta T is 40 into 1 into 10 raised by minus 5. So it is 4 into 10 raised by minus 4. No? So one division will become 1 millimeter into 1 plus alpha delta T. No? Is the calculation clear, beta? Okay. And Nikita, this one is clear, na? That the length has become 6,000.48 millimeters. No? Okay. So now you can see that what I predicted just from the concept of error will become correct over here. The true length is how much? It is 6,000.48 millimeters. The measured length, the measurement is coming out to be 5998, sorry, millimeters. Okay, approximately. So the error is an error of how much? It is minus 2.48 millimeter का error हो रहा है. So the percentage error is this upon, we can approximately take it as 6,000 only, 200. So this you will see is an approximately a 0.04%, but a negative error, okay, because it's showing you a lesser length. Okay. So the percentage error in measurement is on the negative side by 0.04%. So this we didn't need to do the calculation, because what we know is that the least count, which is supposed to be 1 millimeter, this has lost accuracy by expanding by 0.04%. So obviously the measurement, any measurement that it does, it will have a 0.04% negative error, because your least count has increased by 0.04%. So this should have been obvious. We would not have to do this calculation. That is the point I was trying to make over here. Is it clear, people? So this concept of error propagation is very important over here. It can save you a lot of time and hassle in these type of questions. Okay. So now next you will see another type of situation where we will see that this concept of percentage error and error propagation becomes very important. Now this is the most standard thing, a pendulum clock. The time period of the pendulum is dependent on the length of the pendulum. So if you have a metallic pendulum, which is typically the case, it expands on a summer day or contracts on a winter day. And as a result of that, the pendulum clock will tend to either lose time or gain time. So let's understand how this happens. Okay. So a grandfather clock, which again, don't know, you may or may not have seen. If you haven't seen one in real life, which is understandable because these are out of fashion now, you can just search on YouTube and you'll get a good video about the working principle and design and all that of various grandfather clocks. One of the famous brands was West End in the previous millennium. In the 20th century, they used to make grandfather clocks with a metallic pendulum. Okay. Is calibrated to keep time accurately at, let's say, 20 degrees C. If alpha for the metal of the pendulum is, let us say, 8 into 10 raised power minus 6 per degree C, find the percentage error in its timekeeping at a temperature of, let us say, 60 degrees C, and B, the time gained or lost by it per day at 60 degrees C. If the clock is operating at a temperature of 60 degrees C, per day, how much time it loses or gains. Okay. Now here the concept we will use is that if you have a simple pendulum, then you might have seen this formula, the time period of the pendulum. Now generally we write time period with capital T, but here I'll write it with small t because capital T I'm using for temperature, is given by this formula 2 pi under root L by G. Even if you don't have a simple pendulum, but you have what is called a physical pendulum. So a physical pendulum is basically a rigid body. A simple pendulum is a thread plus a bob. But a physical pendulum is more like, a rod with some kind of disc below like this. So it's basically, it consists of a heavy rod plus disc kind of structure, that kind of thing. So physical pendulum will also have a time period, which will be a different formula, but the dependence of time period on the length will still be this. It will be proportional to square root of the length. Length of what? The length of the structure. It will be proportional to square root of the length of this structure for a compound pendulum or a physical pendulum also. Whereas a simple pendulum just consists of a thread with a bob attached. So the length in that is nothing but the length of the thread. So for simple pendulum, you have an exact formula. For a physical pendulum, the formula will depend on various other factors, but it will also depend on the dependence on length will be that of square root. Time period will be proportional to the length of the pendulum to the power half. What other factors there are, that depends on something called moment of inertia and position of center of mass. So we'll be learning those in your further mechanics chapters like rotational mechanics, etc. So we have to use this fact. This is the concept we have to use to solve these two parts. Just try this out now. So remember what I told you about propagation of error. You have to use the concept of propagation of error here. Yeah, Ayush, it is something to do with gravity only. Okay. It is to do with gravity also, and it is also to do with another relativistic effect actually, because the satellite is at a tremendous speed compared to the Earth's surface now. So the satellite is moving at a tremendous speed. So there is a relativistic effect also. Okay, let's understand this. So what is happening is that the length of the pendulum, it is expanding by how much? From 20 to 60 degrees C. So delta T is 40 degrees C, and alpha is 8 into 10 raised power minus 6. So the fractional change in length for us is becoming 40 into 8 into 10 raised power minus 6. So 3.2 into 10 raised power minus 4. Okay. Or there is a 0.32%. 0.032%, sorry. Okay. So this is our delta L by L percentage. So if there's a 0.032% expansion, that means the time period of a pendulum, the time period is proportional to L to the power half. So the fractional change in time period will become half the fractional change in length. So the time period will increase by 0.016% increase in time period. Okay. So the time period increases, the pendulum takes more time to oscillate. So in a given period of time, the number of oscillations that happen will decrease. No? So it will lose time. It will be behind in time. So because the time period is increasing, so basically the least count of the pendulum or the clock using the pendulum, the least count is increasing. So it loses time. Therefore, the clock will lose time. That is, it will run behind the actual time by 0.016%. Okay. So therefore, in one day, how much time it will lose? It will lose 0.016 by 100 of these many seconds. So let's see how much that works out to be. So by my calculations, it's losing up to 13.8 seconds. So per day, it loses 13.8 seconds. You can just check my calculation once, but this is what I'm getting. Yeah. So it's quite a sizable amount of time, which is why clocks are not designed this way. The pendulums are designed very carefully with combinations of rods of different materials and alloys, so that the expansion is not so significant. Otherwise, on a daily or weekly basis, it can lose very significant amount of time. uh, yeah, it is like, you can say it is nearly 100% accurate. Quartz technology, digital clocks there. So what they have is, they have a mechanism by which they compensate for any loss in time. For example, even the mechanical clocks today, they have a mechanism by which you don't need to, for example, you don't need to wind the clock like you used to wind a clock earlier. Up to let's say 2 decades ago, all mechanical clocks had to be wound every day or once a week or something like that, because to overcome the loss in energy by dissipative forces, you have to store some kind of potential energy in the spring system of the clock. Now, today's mechanical watches, they, yes, automatically, that technology is called the psychokinetic technology. So if you're wearing a wristwatch which is mechanical, for example, your hand movement, the kinetic energy generated from your hand movement is captured as mechanical energy in the clock's mechanical system, and that is used to compensate for the loss in energy that happens because of dissipative forces. So it's very, very advanced technology, and there is hardly any loss of time. Yes, it's correct to say that they automatically wind themselves by hand movement. That's one way to put it. Yes. Okay. So this is something important to remember. Okay, for JEE level questions, that you can directly calculate the time lost or time gained like this. That fractional change in length of the pendulum is alpha delta t. So therefore, if time period is proportional to L to the power half, that means the fractional change in time period will become half of alpha delta t. Okay, or the percentage change in time period, delta t by t percentage, will become half of delta L by L percentage. That will become half of alpha delta t divided, sorry, into 100. So this is a useful formula. You can just think of it directly. Okay. So if the time period increases by a certain percentage, the clock will lose time by that much percentage. If the pendulum contracts and so the time period the time period decreases by a certain percentage, then the clock will instead gain time. So for a positive value of delta t by t, the clock loses time, and for a negative value of delta t by t, the clock gains time. Okay. So this is the simple fact to remember. Okay. Now I was telling you earlier that coefficient of surface expansion is equal to twice of alpha, and the coefficient of volume expansion is equal to 3 times alpha. Let's understand how that works out. So you have a surface like this, let's say, which is L into B, okay, at temperature T naught. Okay. So now when I increase the temperature, it is going to expand. Just a second. Yeah. So when I increase the temperature now, let's say to T prime equal to T naught plus delta T, the length has become L plus delta L. Okay. And the width has become B plus delta B. So I have T equal to T naught, L is equal to L, B is equal to B. Now when I increase the temperature to T naught plus delta T, the new length has become L plus delta L. Okay. So that is L into 1 plus alpha delta T. And the new width B prime has become B plus delta B, which will become original width into 1 plus alpha into delta T. Okay, that we can understand. These are both coming from the fact that change in any length dimension is alpha delta T. Okay. So L is also a length dimension. B is also a length dimension. It's the width, which is also length dimension. So both these change according to this principle. So both of these come by this formula. So now if we talk about the area, and the same instance now, let us talk about the surface area of this rectangular plate. Okay. So the original area was L into B. Now here the new area will become new length into new width. So that is becoming, as you can see, L into B into 1 plus alpha delta T whole square. So the new area, which is E plus delta A, is becoming the old area, because L into B was the old area, into 1 plus alpha delta T whole square. Okay, now the small change approximation thing comes in. So this is here. Okay, now the thing is that you know that alpha delta T is obviously very small compared to 1. So 1 plus alpha delta T to the power 2 will be approximated as 1 plus 2 alpha delta T. This is a binomial approximation. Okay, so next step, our new area is A plus delta A, that is becoming A into 1 plus 2 times alpha delta T by this approximation. Okay. And this is what we would write as beta delta T, that is becoming 2 times alpha delta T. So you can see that therefore beta by definition is twice of alpha. So you can just think of it like error propagation. Any surface dimension is the product of two length dimensions. So if you write any surface area as L into B, then obviously delta E by A will become delta L by L plus delta B by B. So this is also alpha delta T, this is also alpha delta T, and this is beta delta T. That's how you get this. So it's a very simple logic actually, why the value of beta is always double of the value of alpha. Okay, so as you can see, this is a very simple logic. Why beta is equal to 2 times alpha. And likewise, now if you apply this to volume, any three-dimensional volume, it will expand according to that principle. If this has length L, width B, and height H, so you can see that volume is equal to length into width into height. Okay, so delta V by V will be delta L by L plus delta B by B plus delta H by H. So that is alpha delta T plus alpha delta T. So by that same kind of logic, the fractional change in volume, which is coefficient of volume expansion into change in temperature, is 3 times the coefficient of linear expansion into this. Okay. Or you can take the case of volume of a sphere, 4 by 3 pi r cube. So volume is proportional to r cube. So delta V by V is 3 times delta r by r. So that also gives you the same. Okay, so this is about this is about thermal expansion of materials. Okay, so we will wind off the lecture here today. Now, next time we will look at along with doubts from the major test, which will take up some time. We'll also look at calorimetry. So in calorimetry, we will look at the concept of specific heat capacity, and latent heat. Okay, and the principle of calorimetry itself, and the working of a calorimeter, which is an apparatus used to do calorimetric measurements. So just do a bit of theory reading from any book like NCRT or Resnick Halliday or whatever about calorimetry and these specific terms. Okay, the definition and meaning of these terms: specific heat capacity, latent heat, calorimeter, even the definition of heat capacity. Actually, before you come to specific heat capacity, the definition of heat capacity, etc. And if you want to do some pre-reading for the chapters coming up, then now is a good time to read about kinetic theory of gases. Okay, the derivations and the principle of kinetic theory of gases, because that's again something we'll be looking at over the next 2 or 3 weeks very carefully. Okay, so that's it for today's session, people. Wish you all the best. You can do questions from thermal expansion from your module. You will be using most of these tricks that I've discussed about propagation of error and percentage error concept and all these things. The rest, the formula is very simple, that fractional change is equal to coefficient multiplied by change in temperature. So that's the universal principle. Okay, so that's it for today's session, people. Wish you all the best.